Greetings. I'd like to talk about issues in excess heat experiments, taking advantage of data from previous years. So Fleischmann and Pons announced their discovery a little bit more than 30 years ago at this point. Let's talk a little bit about the Fleischmann and Pons experiment. Here's Fleischmann and Pons, and here's their cell. You can see there's a cathode rod in the middle wrapped around. There's a platinum anode. It's heavy water electrochemistry. What they published in 1990 was an example of a substantial excess heat effect. And here it is. The excess power is much larger than the input electrochemical power, a factor of about 20 in this experiment. Roughly 630 kilojoules were released in 60 hours, which corresponds to about 2.9 watts for a total of 630 kilojoules. I point out that you would get 1.2 kilojoules had you replaced their cathode with an equivalent volume of TNT and detonated it. So substantial temperature increase corresponding to a large amount of energy, no commensurate chemical products. Also, if it's nuclear, no commensurate nuclear radiation. If real, then this suggests there's a new small-scale clean nuclear energy source possible, which would be of interest given problems that the planet has at the moment. The experiment raises a variety of issues. For example, is the effect real? Is it nuclear? How does it work? And for the purpose of economics, can it work in a cathode cheaper than palladium? Also, how does it work? Fusion is generally understood to require high temperatures, and when fusion, DD fusion occurs, usually you get neutrons. So the question is, what's different about the Fleischmann-Pons experiment? So in a very simple-minded, boneheaded perspective, electrochemical loading of the lattice brings deuterium from heavy water molecules. There's surface reactions. Vollmer reaction brings the deuterium in. It goes interstitial, which I've indicated in the checkerboard here. Palladium atoms, deuterium atoms. In 3 dimensions, palladium deuteride has an FCC structure. The big ones are palladium, small ones deuterium. As you can see, the deuterium's not particularly close in the lattice. So let's think about this so far. Cannot overemphasize the importance of this if it's real. You get solutions to the energy problem, the climate change problem, the clean water problem, robotics, space travel, and lots of other things. If the experiment's real, it says we are missing important aspects of nuclear physics and solid state physics. This experiment would have a gigantic impact on society and on science. Is it real? Well, how do you know if it's real? Can other people see it? So back in 1989, an early experiment, SRI, saw excess heat at the 1 to 2 watt level here. At Los Alamos, Ed Storms reported seeing excess heat at the multiple watt level. IMRA, Japan, working with fuel cells, saw a correlation of excess heat with current. Higher current density, they see more excess heat. At SRI, they built a flow calorimeter in response to the criticism that isoparabolic calorimetry got. The idea is that water goes in, loops around, comes out, and gets measured. You measure the temperature in, the temperature out, the flow rate, and the heat capacity, and you can figure out the thermal power. Here's an example of what was observed. Two of these calorimeters were run in parallel. The blue is light water, the red is heavy water. The green line here is the current density. They use current steps, which seem to help get them excess heat bursts. In any event, the bottom line is there are many hundreds, many parentheses, hundreds of observations of excess heat effect. For my nickel, it's real. Fleischmann reported, or his initial conjecture is that deuterium was fusing in some new way to make helium-4, and he could see the energy output as heat. If so, can we see the helium? Miles, Bush, and Legowski were the first to report observations of helium in a helium link-tight system under conditions where excess heat was made. This is data from a later experiment reported by Godsey. What's interesting is that there's excess heat bursts showing up, and there's a time correlation with the helium that's measured, which was the shocking and stunning result. The amount of helium observed here would be on the order of a third to 80%, depending on the burst. Different amount of burst corresponds to different amount of helium-4. So you would expect, or you would hope, that the amount of helium showing up would correspond to the mass difference when compared with the energy produced. So the question, is this consistent with experiment? At SRI, case cell was run in as a gas cell catalyst, and helium was seen, energy was observed, and from the ratio, the Q value was on the order of 31 MeV with large error bars here. What this means is there's not enough helium being measured to correspond to 24 MeV. So the question is, where is it? And this was true in the experimental Gauss-C measured discussed earlier. And some of the bursts had the right amount of helium. Most of them had much less, between 10% and half. So the idea, the conjecture is that the helium-4, some of it stays in the cathode, and you have to do some work to get all of it out to measure it. At SRI, there's an experiment that'll be of interest to us later, but there's the data points and there's a couple of heat bursts. Now this M4 experiment was done in a helium link-tight mass flow calorimeter. Measurements of the helium was done. This is the helium concentration. This line is what you would hope to be consistent with the energy produced. The initial measurement gave 62% of the amount of helium that was hoped for based on the energy produced, which is in the ballpark of what other people would see. A second sample was taken, a little bit more helium was seen. The cathode was run anodically, it was heated up, more helium was seen. And if you add up all the helium that was seen, it was basically spot on what would be expected from the mass difference and from the energy produced. There's one other experiment of this kind that was carried out at Frascati, where they made an effort to scrub the helium out. In that case, they got consistency within roughly 10%. Fleischmann proposed D plus D going to 24 to 4 helium, an alpha particle plus 24 MeV heat. If so, normally in nuclear reactions, you measure what goes in, what comes out. And from the measurements of the products, you get to an understanding of kinematics. So a basic question is, how much energy does the alpha particle, helium-4, how much is it born with? Now, silicon surface barrier detectors could be used in principle to measure the energy of energetic alpha. Unfortunately, you can't stick a silicon surface barrier inside a electrochemical cell. CR39 detectors have been used in connection with the electrochemical experiments, but you have other issues. The brainstorm here is to let the palladium deuteride itself be your detector. So if you send in an alpha, if the alpha's got enough energy, it can disintegrate a deuteron, and then you would see neutrons coming out. And if the alpha has lower energy, it would hit a deuteron, which would bang into another deuteron. If it has enough energy, it would fuse and give you a fusion neutron. So the yield associated with palladium deuteride as a detector can be evaluated. This is my evaluation. The 3 lines corresponds to assumptions about screening. The red line is no screening. The blue line is, as I recall, 400 electron volt screening, and that's 800 electron volt screening. The right answer is probably between blue and red. There are a number of experiments where excess heat is seen. Here's excess heat, and neutrons were measured. In the Takahashi's experiment with a high current, low current, high-low protocol. So when you run at high current, you can get excess heat. When you run at low current, you tend not to see excess heat, but you can see neutrons during the low current. So the neutrons and the excess heat are anti-correlated in this experiment. If we plot this experiment along with a set of others, we can basically get an upper limit as to how much energy the alpha particle has when it's born. In this case, probably something under 10 keV is consistent with the measurements that have been done. This is shocking. You have 24 MeV being made, less than 10 keV if it's going into the alpha. There was much interest early on in triggering. How do you get the experiment to go? I suggested that you needed phonons present to get things started, thinking about the laser, phonon laser analogy. And the thought was that a deuterium flux can make phonons. So going back to this N4 experiment, I draw your attention to the squares here, which are the diamonds, which are the data, and the green line is a predictor, which is based in part on the flux of deuterium going through the surface. That flux would make terahertz vibrations through the surface. And in this experiment, there's a very strong correlation between the excess heat produced and that flux. The energetics group used super waves as a way to load their cathode. The idea I had is that if you have a drawer that's stuck, if you shake it and move it faster when you're shaking more strongly, then you can unstick the drawer and get it open. In essence, that's what these super waves are doing. And in one experiment here, roughly 1 or 2 watts go in, on the order of 20, 25 watts come out. The power gain in this experiment was in the neighborhood of 25. In Swartz's fuser experiment, the loading occurs locally because he's got a very anti-symmetric, he's got an anode that's located here. It doesn't surround the coil. So the hydrogen or deuterium goes in this case, deuterium goes in localized, but then it can leave everywhere else, which sort of maximizes the deuterium flux in. Where does the energy go? I was thinking maybe it goes into vibrations. The question is, can this be tested, or is there experimental evidence for it? Let's develop a 2-laser experiment where cathode and in this experiment, if there had been no lasers and if he turned the current up, he would have produced excess heat. What he does is he cranks the current down a little bit below where you get excess heat and then turns both lasers on, or one laser or the other laser. And what's seen is that if both lasers are on, if the laser polarization is correct, it can initiate an excess heat burst. Not only that, for this experiment, when the heat burst turns on, it stays on. even when the lasers are turned off. And the result here is consistent with an interpretation of the nuclear energies going back into the mode. The lasers are tuned at slightly different frequencies, so there's a beat frequency. And this was the point of the experiments initially envisioned, that you can, by tuning the beat frequency, you can scan across frequency. And in this case, 3 sweet spots were seen. The lower energy one seems to correspond to the gamma point for the optical phonons. The higher one seems to, or the middle one seems to correspond to the L point for the palladium deuteride optical phonons. This high point is not immediately obvious. So for example, here's the gamma point, here's the L point for the terahertz phonons in palladium deuteride, but these things don't go up to 21 terahertz. On the other hand, if there's some hydrogen in as an impurity, and given that this thing is not sealed against air and it's humid when the experiments are done, the theoretical value for the L point for the hydrogen as an impurity in a mixed system is somewhere near 20 terahertz, suggesting that this might be a candidate for accounting for the third peak. Okay, so the LETS-2 laser experiment provides indirect evidence of energy going in phonons. Mitchell Swartz did a really interesting experiment where he's got a reference laser and he's got a second laser to take data with. He's got this home-built grating and detector. And he's running with a nanner and seeing excess heat with a nanner. So if there's no current drive and no excess heat with a nanner, then he gets the Rayleigh scattered radiation at 532, and he sees a Stokes shifted peak, which basically is what happens when the 532 light comes in and causes the excitation of an optical phonon. So if your optical phonons are cold, then energy will go in. If your optical phonons were hot, on the other side, they would be giving you some scattered radiation. And if you look down here, maybe there's some hints of some bumps or something, but largely there's no anti-Stokes peak here. When he runs with the current on under conditions where he's getting excess heat, then the spectrum looks like this. He gets a Stokes shifted peak here, but he sees an anti-Stokes shifted peak, and the anti-Stokes shifted peak is big. So this tells you that there's very strong terahertz vibrations going on. The fact that the anti-Stokes line is basically in some experiments competing and stronger than the Rayleigh line tells you that the vibrations are very strong, and is suggesting that this the conjecture that the nuclear energy is going to vibrations has got some non-trivial support in these experiments. Loading. So how do you get the deuterium into the lattice? There's electrochemical loading, fuel cell, molten salt, gas loading on beam glow discharge loading. And basically all of these have been studied. Excess heat was seen in fuel cell anodes when you fuel cell experiments where you load you have overpressure deuterium in the gas. So it helps the loading in the cathode, or in this case anode. In these experiments, excess heat was seen to increase with loading above loading about 0.3, and increase with current above about 100 milliamps per square centimeter. Molten salt experiment by Liao and company. Excess heat was observed in these experiments. Glow discharge experiments at Luch. I went and visited this thing. It was quite an experiment. Here's some data they reported of a fair amount of claimed excess power. So the idea is that you don't need to do electrochemistry, only other ways of getting hydrogen or deuterium into a cathode or metal sample is interesting. Loading requirements. At the beginning, in 1989, there was resistance ratio loading curve available for palladium hydride, palladium deuteride, two curves. And basically, when you get to a modest loading, the resistance ratio turns over. In earlier days, people measured resistance ratios in alloys as a sign of order. The resistance lower for the ordered system. If you have a 50-50 alloy, typically that would give you the largest resistance. And it'll come back down when you get to be ordered again. In this case, it sort of works a little bit like that, but it doesn't come down quite as much. The calibration was redone. There's calibration for palladium hydride, and in this case, the resistance ratio high loading is seeming to come down very close to 1. In palladium deuteride, it's much closer to 1, but armed with these resistance ratio curves, then you can monitor how much deuterium's in your cathode. In this experiment, excess heat is correlated with loading. I think this one's the SRI data. And one can see that above loading, about 0.85 or so, excess heat increases with loading. In the superwave experiments at energetics, the loading it's very hard to get high loading because you need a very high equivalent pressures. You need to get somewhere in the neighborhood of a gigapascal equivalent pressure to get the loading near 1. In this case, the superwaves gets extremely high loading, and the resistance ratio is down in the neighborhood of 1.3 to 1.4. When McCoubrey surveyed the positive results, he found that at SRI, cathodes which reached the peak loading well above at least 0.9 deuterium per palladium or higher were able to show excess heat, and a similar result at NEF Scotty was seen. In the early days, the Caltech loading was very low, the MIT was very low, and no positive results were observed for those experiments. Back in the early days, the claim was that these were not reproducible. You go back and you look at the published literature, you can find over 200 papers with negative experimental results. And this provided the basis for rejection of the research as not being part of science. If you read those papers and you say, well, how many of them actually involved electrochemistry with a palladium cathode and some measurement of temperature, the number is much fewer. If you start with these experiments where electrochemistry was done and something like the Fleischmann-Pons experiment was attempted, you could say, did the experimentalists learn from what Fleischmann was arguing, that you needed high loading? And so if we ask how many of these 39 negative results of loading even mentioned, we're now down to 22. Now, mentioning loading is good, that's a positive, but you'd actually like to get the loading to be at least 0.83 to have any chance. And if you follow the results at SRI, it had to have reached about 0.95 to have any possibility of seeing aqueous heat. Well, 7 of these papers reached a loading, reported loading of at least 0.83. Only 2 of them got to loading of 0.9, and none of them reached conditions where it would have expected excess heat. So the argument that the experiment's not reproducible is repeated, was started back in 1989, basically May 1st at the Baltimore EPS meeting, and has become part of established canon. And the initial arguments were just bad. High pressure loading can be achieved at low temperature at in a very high pressure diamond anvil cells. Um, Two experiments here reached very high loading. No excess heat was seen at all. So we concluded that more than just high loading is required to see excess heat. Green and Quicketen did an electrochemical experiment and achieved very high loading, trying as close as they could to follow the early SRI work. They got no excess heat. You can see here. This is probably the best of the early negative results. A minor issue is that at SRI, they use current ramps as a way to stimulate excess heat bursts, whereas Green and Quicketen kept their current absolutely flat and constant, which at SRI at the time would produce no excess heat as well. There have been many negative experiments. At SRI, a very large number of negative excess heat experiments were carried out in connection with the Navy project. The reason for it appears to be the reliance on 5-9 purity palladium. Impure palladium seems to work much better. A very large number of negative results at coalescence. They closed their doors and gave up with absence of positive results. The experiment's not completely understood at this point. Question is, where did the reactions occur? In palladium deuteride, the DD spacing is large, and experiments suggest that palladium deuteride is inert. On the other hand, if you have a vacancy, you have the possibility of getting a lower electron density. The issue is that deuterium occupies an octahedral site, basically because the electron density is close to what the deuterium wants to see. A D2 molecule could form a lower electron density. This would be the density that D2 or H2 would see near palladium nucleus. So near a vacancy, the idea is that you have electron density low enough to have the possibility of having Ds come together. Loading in the vicinity of monovacancy was studied by Nazaroff and company. And basically, the simplest way to explain it is there's O sites and there's T sites, and they're essentially degenerate at low loading. When the loading gets high enough that you start to have neighboring O sites and T sites, then there's a price to be paid. It costs, my recollection is about 50 millivolts or so for each pair. So once you get 9 or more deuterium in a monovacancy, then you have neighboring O sites and T sites occupied. Now, that by itself, in my view, isn't great because O sites and T sites are still pretty far apart. On the other hand, deuterium or hydrogen next to palladium or nickel has a possibility of forming a dideuterium configuration with inter-deuteron spacing on the order of an angstrom or perhaps a little bit less. Excess heat was seen in palladium initially with Fleischmann ponds, but later on, titanium, nickel, gold, if we believe the observations of weight, even steel. So I think what's special about palladium is its ability to have dideuterium or dihydrogen form next to it, which is shared by nickel to a lesser degree by gold. With respect to titanium and iron, the situation's not clear at this point. Hydrogen, Mills and Kinesis showed excess heat or claimed excess heat in nickel cathode and light water electrochemistry. Other people subsequently followed up. Piantelli has a shocking set of experiments with nickel bar and hydrogen gas, and there's been many others. In the Piantelli experiment would run in hydrogen near 1 atmosphere. Basically, you had a protocol where you run it in, pump it out, run in, pump it out, run in, pump it out. Nickel doesn't absorb hydrogen very well under normal conditions. What Piantelli saw is that each of his loading cycles, the amount absorbed would increase. And the only reason that could happen is something's changed inside the nickel lattice. I'm of the opinion that he's creating monovacancies, and that the vacancies are acting as traps. And so he's once he's prepared, uh, uh, then in order to stimulate excess heat burst, he does a temperature cycling. Basically drives it in and drives it out, and you can imagine that that's going to make a flux of hydrogen going in and out of the system. So that provides phonons. In a sense, the Piantelli experiment can be understood, I think, very similarly to the early SRI palladium dioride experiments. Instead of D2 going to helium-4, I think these experiments are based on HD going to helium-3. Mizuno did aqueous plasma electrolysis. I draw attention to this experiment because in this case, over a relatively short time, there was a prodigious release of excess power. And tungsten, again, light water experiment. So this is showing that the light water system is active. The cell exploded, and my understanding is Mizuno's eyebrows got singed in the process, but he got some data, which was shocking. So we have some measurements of helium-4 correlated with the excess heat. For the case of light water experiments, if helium-3 is going on, then we would love to see a measurement of helium-3 from a light water experiment correlated with excess heat. There was an attempt made here. Alexandrov's working on it currently. We absolutely, desperately would like to have a confirmation of helium-3 signal from a light water experiment. Arata proposed nanostructured nanostructured palladium as a host for basically excess heat experiments. This was pursued by Japanese effort under Takahashi for many years, starting in, so I recall, 2005, 2006 or something, continues on to the present. Basically, in a more recent version experiment, they load the nano powder in, they flow in either deuterium or hydrogen, and basically the heat starts being produced, and you get a temperature rise. So here's some data from palladium nickel in a zirconium oxide matrix. And there's excess heat showing up at the 15 watt level. Recently, they got some funding to scale up their experiments to involve more mass. And they've been running at a high temperature. In this experiment, they're getting basically reproducible sustained excess power at 70 watts. And this has the potential for being turned into a commercial prototype, which is one of the things that they're interested in working towards. Mitchell Swartz has been studying his nanner, so he's got very similar nano material in the zirconium oxide matrix. So he works with palladium, works with nickel, mixed palladium, nickel, and other stuff as well. And then he's got this arranged electrically as a two-port. Think of it as a resistor, and what he sees is when he runs current through it, he sees excess heat burst. So he can turn the excess heat on and off. So for example, the blue lines down here is the input current. The red line is when the current is going through a resistor. This red line is when it's going through a nanner. So he runs nanner, resistor is a way to calibrate. And in some experiments demoed done at MIT some years ago, 2012, as I recall, 2013, something like that. He saw a power gain of about 14. He's found it's impacted by magnetic fields. He's gotten higher reproducible power gains with that. So what's going on with nano PD? So bulk PD loads something like this, nano PD loads something like that. In various experiments, people have made interesting observations that are relevant. In this case, I keep it all report neutron diffraction, which is sensitive to tetrahedral occupation of deuterium. And they're basically, as they raise the temperature, there's in their nano particles, they're staying this. Now they have a complicated interpretation. I'm going to suggest a slightly different interpretation, that in the nanoparticle, that Fukai's and high loadings, palladium hydride, palladium deuteride, at elevated temperatures, these superabundant vacancies form. I think that this happens much more easily in a nanoparticle, partly due to the surface energy. And in bulk, you don't get occupation of the tetrahedral site. But in around a vacancy, the OSIs are approximately degenerate. So I think this data shows evidence of vacancy formation, highly loaded nanoparticle. Similarly, Liu et al. Sees the X-ray diffraction pattern consistent with superabundant vacancies. And again, I think this is evidence that you've made, when you load these things, that they make vacancies really easy. So the normal bulk FCC looks like this in the Fukai phase. You're missing 1/4 of all the palladium, and it's ordered like this, which gives you this curved structure. In any event, it would be really great to get this issue settled. I'm of the opinion that temperature effect and power. Okay, so Fleisch and Pons reported feedback effect that basically, if you run in the calibration pulse, the temperature before the calibration pulse, the temperature after are the same. When excess power is being made in these experiments, after running excess power pulse, the temperature seemed to be raised. It didn't return to the initial one. So this was called positive feedback. Fleisch and Pons used this to nurse their cells up to producing extreme amounts of excess heat and even boiling in this case. Cravens observed a version of it. Excess heat was being produced, runs in a calibration pulse, and instead of returning back to the initial temperature, the baseline is elevated. So excess heat can be used to increase the heat. Storms measured basically excess heat as a function of temperature. It looks like this, and it's consistent with the Arrhenius law with a barrier energy about 673 millivolts, which is consistent in this case with the helium diffusion barrier in palladium. So the picture is that maybe helium clogs up the active sites, and that's what limits the power. If so, then if you could get the active sites closer to the boundary, you could get rid of helium more efficiently. I proposed this some years ago. Arata at ICS 17 suggested the same thing. Conclusions. Fleisch and Pons experiment finds excess heat. I think it's real. There's been a huge amount of progress in 3 decades and much more to be made. And thank you for your attention.